Okay, exponential functions. Now, as I was saying a while ago, that exponential functions work a little bit differently than any functions that we've had before. Up until now, we've worked with algebraic functions, which is what this first part talks about. Functions with values that are obtained by adding, subtracting, multiplying, or dividing constants and the independent variable, or raising the independent variable to a rational power, like a quadratic or cubic. Those are called algebraic functions. So whenever we work with those, we add, subtract, multiply, divide, whatever. Exponential functions are not algebraic functions, okay? Exponential and logarithmic functions are called transcendental functions. Yeah. Because they cannot be expressed in terms of algebraic operations. They work differently. The way you solve the equations and work with them is different. In fact, you can't solve, unless it's just a really basic algebraic equation, you can't solve it until you know logarithms, okay? So, you know, these kind of functions transcend algebra is one way to look at it. So algebra doesn't work with these. So they work a little bit differently. All right. Zach, what are you doing back there? Yeah.
Take that phone away.
Yeah, I know.
Don't let him tell you what to do.
I'm fixing to.
Hey, you're recording.
Yeah, I know.
Oh my gosh. He was like playing on my phone.
Yeah, where's Miss? Oh, Miss Bleach might want to watch this. Okay. Exponential function. Okay, an exponential function, a basic exponential function has a base and an exponent. But in an exponential function, the exponent is the variable. It's the missing. Okay? So here's some examples. Here's the base. This has a base of 4 raised to the x power. Okay? This one is 1/3 raised to the x power. You can even have a negative exponent. 7 raised to the negative x power. So those are all examples of exponential functions. Now, non-examples. 2x to the negative 3rd power. Well, that's not an exponential function because the variable is not the exponent. 5 to the power of pi. Well, pi is an irrational number, so that's basically like saying 5 to the power of 3 or any other number. And then 1 to the power of x. 1 to the x is not considered exponential because 1 raised to any power is always going to be 1, so it's kind of in a little category by itself. Okay, so we're going to sketch and analyze graphs of exponential functions. We're going to look at them and figure out the domain, the range, the intercepts, the asymptotes. So a lot of things that we talked about earlier in the year are going to come back up. In behavior and where the function's increasing or decreasing. All right, so example 1a. We are going to graph f of x equals 3 to the x power. So the base is 3. The exponent is your unknown, your variable. Okay, so we're going to make a table. And I'm going to let you put this in the calculator, which y is your f of x, which is your 3 to the x. All right, so we're going to do -4, -2, 0, 2, 4. Okay, let's go ahead and talk about, let's just plug these numbers in and talk about what we would get, and then we'll put it in the calculator. Okay, so if I have 3 to the -4th power, okay, 3 to the -4th power is the same as 1 over 3 to the 4th, or you could look at it this way, 1/3 to the 4th power, okay, which would be 1 over 81. If you raise both of those to the fourth power, and 3 to the fourth power, 81. 3 times 3 is 9, times 3 is 27, times 3 is 81. Okay? So 3 to the fourth power is 81. So that'd be 1 over 81. Now somebody put that in your calculator and hit Control Enter and tell me what the decimal is for 1 over 81. So 0.01 basically. All right. Now 3 to the negative second power would be the same as 1/3 squared, which would be what? What's 1/3 squared? 1/3 times 1/3. 1/9. And somebody put that in the calculator. What's the decimal for 1/9?
1.
So 0.11. Now, anytime you raise anything to the 0 power, does anybody remember what you get? No, close. 1. Anything raised to the 0 power is 1. If it's a million raised to the 0 power, it's 1. Okay, now these are easier because if you plug 2 in for x, that would be 3 squared. What's 3 squared? 9. Okay, if you plug in a 4 for x, you get 3 to the fourth. What's 3 to the fourth? That'd be 9 times 9. 81. Okay. So, now I want you to get your calculator and
Well, everybody's calculating for me.
okay,
Oh, that's it.
go to a graph and I want you to put 3 to the x power in. So to be, listen, 3, and then does everybody know how to jump up to the exponent? You use the little housetop looking thing over here. And then just put x as your exponent and hit enter. So you can see what it looks like. So now go look at the table, Control T. And let's see if we were right. X. 3 to the x power. All right, so at -4, look what it is, 0.01. -2, 0.11. 0, 1. 1 is 3. We didn't do 1, but it's 3. 2 is 9, 3, 27, 4, 81. Okay? I guess we should have went ahead and put 1 in there because that would fit on our graph real nicely. All right, so let's graph this. -4. Now, these two right here, the only reason I had you do these two is to show that it's decreasing as you move left. But look at your graph. Does it go below 0? Look at the graph on your calculator. No, it doesn't go below 0. So as it's moving to the left and these numbers are getting smaller and smaller and smaller, it's getting closer and closer to 0 without ever actually getting to 0. Okay? All right, so really the first one we're going to actually graph is 0, 1. Wait. I wanted to count by 2s on this. So 2, so that's going to be wrong. 2, 4, 6, 8, 12, 16. So actually, it's going to be right here because I'm counting by 2s. 4, 6, 8, 10, 12, 14, 16. -2, -4, -6, -8, -10, -12. Okay. All right. And then, even though 1 is not on here, it would be 3, right? 3 to the first power would be 3, which would be like right here. 2, 9. And then 4, even 3 is 27. It won't fit. So that's really all that we can graph. Now I'm going to use a highlighter to connect this because I don't do well with the pen. I think it's because it's so thin. And this is just a sketch anyway. So this looks like right here that it goes completely horizontal, but it really doesn't. It's getting closer and closer to 0. But because the differences, as you get way out here, you're getting, the differences are just minute. So it makes it look to the eye like it's horizontal, but it's really not. Okay, so now we've got that graph. Now we want to analyze it based on all these things. All right, domain. You're going to have to reach back in your brain. Who remembers what domain is? Your possible x values. So when I'm looking at a graph, I think, where does it start on the left and how far does it go to the right?
It's like continuous.
Exactly. It goes forever this way and this way. So the domain in interval notation is negative infinity to infinity, which is all real numbers. Okay, what about range? Good. Range are your possible y's. So in other words, where does it start at the bottom and how high does it go? All right, 0 to infinity. Good. You're ahead of me, Ebony. Good. It's 0 to infinity, but not including 0. So don't use a bracket. Use a parenthesis, whatever. Okay, then it says intercepts. Okay, well, a function can have one or more x-intercepts, but what about this one? Where does it cross x-axis? It doesn't. So this one has none. Now, a function, to be a function, can only have one y-intercept, and this one does have a y-intercept. Where does it cross the y-axis? At 1. So 0, 1. I like to put it as a point. Okay, asymptotes. All right, dig back in the recesses of your brain again. Do you remember what an asymptote is? It's a line. It can be vertical, horizontal, or it can even be a slant asymptote, which not that doesn't touch. It just gets right up and runs right up next to it.
0.
So y equals 0 is our asymptote, which y equals 0 is actually the x-axis. All right, what's next? End behavior. Oh, this gets back to our limits. It's been a while. Okay, when you do end behavior, you're asking yourself, what is the y value doing as x is getting smaller and smaller? So as x is going to negative infinity, what's the y value doing? That's the first part of it. So we write it as a limit. We say the limit, and this is f of x, the limit of f of x as x approaches negative infinity. So this is just about the only time you're actually starting on the right and looking left. Usually you're going from left to right. All right, so from right to left, what's happening to the y value as x is getting smaller and smaller and smaller? The y is, but what's it approaching?
0.
It's getting closer and closer to 0. So the limit of the function as x approaches negative infinity is 0. Okay, now we've got to talk about, well, what happens as x is getting larger and larger, or as it's approaching positive infinity? What's happening to the y? It's going to positive infinity also. And I think there's one more thing it asks for. Where is it increasing or decreasing? Okay, now increasing and decreasing, you're always going from left to right. And functions can have both. It can be increasing in certain areas and decreasing in certain areas. But what about this one? It's just increasing from negative infinity to over the whole domain. It's increasing. So increasing from negative infinity to positive infinity. Therefore, there's no extrema, which is your maximums and minimums. What's going on? Okay. All right. So we're done with that one.
What time are you out here today?
11. All right. Example 1B. We're going to sketch and analyze. I forgot. I gotta do it. Oh, yeah. G of x equals 2 to the negative x power. Now, this is the same thing as 1/2 to the x power. Those are the exact same. So let's do a table. Let's see if we can figure it out without going to the graph first. And it'd be a lot easier to use this one right here, 1/2 to the x. And let's do -6, -4, -2, 0, 2, 4, 6. You won't graph every single one of those, but you can kind of look and see what's happening. So 1/2 raised to the, well, this is kind of weird because it's -6, right? It'd be, so it would be 1/2 to the -6 power, which would be 2 to the 6th. That's kind of confusing, isn't it? Maybe it's easier on this part to go 2 to the -6 power would actually be 2 to the 6th. So what's 2 to the 6th? 64. All right, if you put a -4 in, that's actually 2 to the 4th. What's 2 to the 4th? Okay, if you do 2 to the negative second power, that would be actually 2 squared, which would be 4. All right, 0 is neither positive nor negative, so basically 2 to the 0 power would be 1. Okay, now move over here to this one. 1/2 squared would be,
Who is that?
I don't know, but if they're not opening the door, evidently they don't need us. Okay. 1/2 squared would be what? 1/4? One half to the 4th would be 1/16. What's the decimal for 1/16, somebody? So 0.06. And then this would be 1/2 to the 6th power. So 1/64. Somebody do that one on a calculator.
0.015.
Okay. So 0.02 basically. And we could keep going. And what you're going to see is these decimals would just keep getting smaller and smaller and smaller, but actually never reach 0. Okay. So now if you want to go to your calculator and put, let's just do that. Because I want to show you something else anyway. I want to dot B, just clear all this out. Okay. So we have 2 to the negative x. Enter. There's what it looks like. Now, before I do the table, I'm going to go back. And an F2 of x, you don't have to do this, but I just want to show you something. I'm going to put 1/2 to the x power. And what do you think is going to happen? It'll be right on top of it. There it is. Okay, because they're the same. All right, so let's check our table since we're here. -6 was 64, -4 was 16, -2 Okay, it looks like we did it right. Now look, as we get bigger and bigger and bigger, look what's happening to those y values. See what they're doing? Okay. All right. Now let's graph it. Of course, we can't do negative. Oh, we're going to count by twos again. Okay. So negative 4, 16 I can graph. Negative 2, 4 I can graph. Or 0, 1. And then 2.25. And then from there, it just gets closer and closer to 0. Okay. Now let's analyze this one. Let me get my camera back up over here where I can see it. Okay, domain. Is that different than the one previous?
No.
No, it still goes from negative infinity to infinity. So that one's the same as the one we did before. What's different about this one anyway, when you look at it? It's a lot flipped. Yeah, it looks like it's flipped. All right, what about the range? Did it change, or is it still 0 to infinity?
No, it's infinity.
No, you always start with the low.
Oh, so it's 0 to.
Yeah. All right, what was the next thing? Intercepts. X-intercept. Or x-intercepts, do we have any? No, still don't have any x-intercepts. Now, what will happen is if you could have an x-intercept if the graph has been moved down, if it's a transform graph that's been moved down. All right, what about y-intercept? So 0, 1 again. So that stayed the same, didn't it? Even though it's going the other direction. Okay, what's next? Asymptote? What's our asymptote? Yeah, but what is the asymptote here? Is it the same one we had before? Yeah, it's still the x-axis, which is y equals 0. Now what, in behavior? So, now the behavior is going to be a little bit different. Because the limit, and this is g of x, the limit of g of x is x approaches negative infinity. So as we're going this way, what's y doing? It's going towards infinity, isn't it? Now, on the other one, when we were going that way to the left, it was going towards 0. But this one's opposite. So then our limit of g of x as x approaches positive infinity. So as we're moving to the right, what's it approaching? 0. So those flip-flopped from the one on the other side. And then increasing, decreasing. Decreasing over the whole domain. So decreasing from negative infinity to infinity. So that was different. The other one was increasing. Now, you may have talked about these kind of graphs in one of your science classes. Have you ever heard of exponential growth and decay? Mm-hmm. That's what these two graphs are, two that we just did. The first one, 3 to the x, is an exponential growth. Okay, it's increasing. Now, notice, When you're way out here, it's increasing just barely, way out here. But as you come in here, it starts increasing rapid, it gets faster. And then when it gets up here, it's increasing so much that it almost goes vertical. Okay, there's huge jumps. So little bitty jumps over here to huge jumps when you get way out here. Okay? All right, so look at what we talked about. Domain, range, the y-intercept, I like to use 0, 1, not just 1. X-intercept, none. Extrema, we didn't talk about that, but there's not any. Extrema would be when it goes from increasing to decreasing or vice versa. Maximums and minimums. Asymptote is the x-axis, which is y equals 0. There's your limits. It's continuous, and it's also increasing over the whole domain. And notice, if you have an exponential growth, your base is going to be like greater than 1. So we had 3 to the x. So you can tell by looking at a function if it's going to be exponential growth or decay without actually having to have the graph. You just look at what the base is. All right, so over here, all the things that we already talked about. Of course, this is 0, 1, y equals 0, decreasing. And your base on an exponential decay is going to be a fraction. And it has to be a positive exponent to be able to see that. Okay. So if it's a number raised to a negative exponent, then your actual base is a fraction. So that's why this one's an exponential decay. Okay. All right. And also, there's a note here that if you have a number in front of your base, that's where your y-intercept is going to be. The y-intercept for both of these was 0, 1, or 1. So that means the coefficient in front of the base, if there was one, of course there's not one, would be 1. If you wanted to put one in, you'd have to do it like this, of course, and put a 1 out front. But that'll make more sense here in a minute when we do some transformations. Okay? All right. I'm not going to stop just yet. I'm going to have you do one thing, but we're not going to get into these yet. We're going to do some transformations, but the base graph that we're using is 2 to the x. So what I want to do is I want to graph 2 to the x on all 3 of these, because we want the base function, and then we'll graph the transformation on top of it. Okay? So 2 to the x, and we're not going to count by 2's on this. You can put this in the calculator if you want to, or we can just sit here and do it by hand. 2 to the negative second power. That would be 1/2 squared. That would be 0.25, right? 1/4. Negative 1. 2 to the negative first power would be 1/2 to the first power, which would be 1/2 or 0.5. 2 to the 0 power would be what? 1. Good. 2 to the first power would be what? 2. 2 to the second power would be what? That'd be 2 squared. 2 to the third power would be what? 2 times 2 times 2. That's probably enough. Okay. So, negative 2, 0.25. Negative 1, 0.5. 0, 1. 1, 2. 2, 4. 3, 8. So I'm graphing it in blue. So this is f of x equals 2 to the x. So we're going to graph that on all three of these. Now, when you get to this one down here where you have all four quadrants, it may look a little different, but same thing. So at least when we come back tomorrow, we'll have these already graphed. On this one, the one at the bottom, your 3/8 is going to be all the way at the top. Okay, we'll stop right there for today.